Hi everybody, and welcome to the webinar. Today I'm going to talk about our Ion Beam Etch tool that's specifically configured for delayering of semiconductor chips. So just a little bit of background about Denton Vacuum. Founded in 1964 by Richard Denton and currently operating a 50,000 square foot facility just outside of Philadelphia in New Jersey. And we make all sorts of capital equipment for coating and deposition, including ion beam, sputtering, and evaporation. All right, now I'm going to talk about the tool configuration and how it's been optimized for delayering. So to start with, it's based around a 14 centimeter RF ICP source. So this source is very broad beam. The beam itself is actually 14 centimeters with about plus or minus 3% uniformity. And the advantage of that is you can delayer an entire chip uniformly. So on top of that, we have added the secondary ion mass spectrometer so that as you etch through the layers, you can observe like when the copper traces go up and down and stop exactly where you need to, whether that's in a metal layer or a via layer or other. So the substrate stage is water cooled to keep the chip cool during etching. It takes wafers up to 100 millimeters, although typically you're just mounting a single piece in the center. Has rotation from 10 to 50 RPM, and the tilt angle goes fully from 0 degrees, which is facing the source, to 90 degrees, fully perpendicular to the source. And I'll show later why that's important in order to control the selectivity and get a planar etch across the whole chip. So the tool is turbo pumped, which means it can be compatible with reactive and corrosive gases instead of the usual argon, and it has a single wafer load lock. And the whole tool has full computer automation, including recipes that use the sims for endpointing. So here's a diagram of how an RFICP source works. In the center is a quartz discharge chamber that contains the plasma. This is advantageous because the plasma is fully remote from the substrate, which means it's unaffected by anything that's going on by the etching. The result is that even if you etch on time alone, you get repeatability of better than 1%. So around the outside of that is the RF coils. Those keep the plasma lit. And on the front are the grids. So the grids pull the ions out of the plasma. Because you have these grids where you can set the voltages, you can actually independently control the ion energy, which is set by the grid voltage, and the ion current, which would be set by how much RF power you're dumping into the plasma. So this beam is very broad. When it leaves the source, it's around 14 centimeter diameter, and it's a little bit wider by the time it reaches the substrate. And as I said earlier, the uniformity for that is about plus or minus 3% over 100 millimeters. But if you're looking at a single IC just in the center of the chuck, the uniformity is better than 0.1%. What's not shown here is the electron source. So in this tool is a plasma bridge neutralizer, which is filament based. So the source only produces ions, which means it can charge up your sample and stop etching. By having the electron source also in the chamber, everything stays neutral. So one aspect of ion beam etching compared to other methods is that the ion penetration depth is actually not very deep. If you're used to plasma fib or some other techniques that use ions in the range of 10 to 30 kilo electron volts, this is actually quite low. So a typical ion energy we use is 600 electron volts. And this is a simulation done using the TRIM software, which shows that for argon ions of 600 electron volts into a target of silicon dioxide, they only penetrate a mean depth of around 2 nanometers, although some can go as high as 4 nanometers. So that's very thin compared to the thickness of layers, even at advanced node, until you get right down to the device. So that means as you delayer your device using this tool, the layers beneath that you haven't etched yet are preserved electrically. So next, I'm going to talk a little bit about material selectivity. So if you talk about ion etching, a lot of people are familiar with reactive ion etching. And in that case, it's very much a chemical process where the etch rate can be completely different for different materials depending on your gas chemistry. You can have etch selectivity of 10 to 1 or 20 to 1 is common, or you can even push it higher depending on your materials and gases you're using. In this case, when you have an ion beam, the material selectivity, even if you're comparing something like a refractory metal like tungsten and a very soft material like copper, the difference in etch rates might only be a factor of 2 or 3. In order to get that down to 0 so that we can etch in a planar way from the top of the chip down to the lower metal layers, 1 degree of freedom we have is the incident angle. So this is why it's important that the tool tilts from 0 to 90 degrees. So you can see on this chart, which is data that I took, if you go to around 50 degrees to 55 degrees, the etch rate for silicon oxide and copper are the same. So that means if you have copper traces within a silicon oxide matrix, you can simply tilt the machine to 50 degrees and you can keep etching planar through the device. On the right is kind of typical etch rates. So 600 volts and 230 milliamps is not the highest power the machine can go to, but it's on the higher end, but it's a comfortable level where it's very reliable. So in that case, we're getting etch rates of a micron of etch in around 8 to 20 minutes, depending on the angle and the material. So that means you can also do stuff like etching chips through the backside. You can go through 20 microns of material in a reasonable time. So on the prior slide, I showed that you can control the selectivity just by changing the angle, but sometimes that's not enough depending on what material you're using. So this machine is fully capable of using chlorinated gases and fluorinated gases and oxygen. You can put it through the source or you can just introduce it to the chamber, and it comes standard with 6 MFCs. So there's a lot of flexibility in what kind of gases you want to use. Here is some data which shows the effect of adding just a little bit of oxygen to what is our normal argon etch process. So you can see that it dramatically affects the etch rate for certain materials, like copper dropped significantly, whereas for other materials, it either dropped less or even went up in the case of aluminum. Okay, so one of the reasons for introducing reactive gases is because you can often find an angle where 2 different materials have the same etch rate. But once you go to a more complex material system and you're trying to match 3 or more materials together, then there's a possibility of doing that by adding some additional gas. So this tool is equipped with a secondary ion mass spectrometer, and it is directed at the center of rotation of the substrate. So as it goes around, and also as the tilt changes, it can still pick up ions that are being etched. And the purpose of this is to produce a chart, as you can see in the bottom right. So the copper is shown in blue. So as we etch through the material, the copper of M7 is high, it goes low. Then we can pick out M6, 5, 4, 3, 2, and then M1 is less visible as you get to the bottom of the chip. In the lower red trace is tantalum, and you can see every time the copper ends, there's a spike in tantalum from the diffusion barrier. So I just have a couple slides about applications we did. Here's a etching. This is not advanced node, but this is etching down to M1 and stopping and imaging. So in this case, we were able to clearly see the sim signal and stop on M1 based on it. And the result in the top right shows a pretty good result of M1. If you move around the chip and look very closely, you can see that there's a little bit of M2 left in patches, so it's not the perfect result. So here's another result, is very similar, different type of chip. So this chip is very small. It was only 3 millimeters by 3 millimeters, and yet we were still able to pick up enough sim signal to resolve the metal layers. In this case, we also stopped at VO1 and imaged the chip in SEM. Okay, so now let's go to the tool and delayer a chip. The chip I prepared today is sort of a dummy logic chip with alternating copper and silicon layers. And I'm going to set up the tool and we'll watch the SIMS trace as it etches. Okay, so here we are at the tool. I'm going to start by loading the sample, and then I'll talk through the UI while it's pumping to crossover. So I'm going to start by opening the load lock. So when the door opens, the chuck is actually tilted at 22.5 degrees because that's sort of the angle that it needs to be inserted at into the chamber. So it'll come back to be flat, and now it's ready to load. So there is an option here for, like, you can load your wafer and hold it down with vacuum while you attach your clamp ring, but I'm not going to use that today. So this chuck looks kind of messy because we've etched so many variety of samples in here, putting kind of strange stuff in there. Today is going to be more pedestrian. I'm just going to load a very typical piece of silicon, which is very similar to like a logic chip. In fact, we call it a dummy logic chip. So this piece that I'm putting down first is a thermal pad. So we want to have good thermal conduction between the device and the chuck. So that goes down first. Then this piece of silicon wafer, this is just a test grade silicon wafer that we use to protect the chuck from etching. So we want to use silicon here because it has low sputter yield and it's not going to produce a bunch of elements that are going to confuse the SIMs. So you could also use a stainless plate. I wouldn't recommend like an aluminum plate because it's going to etch through it very quickly, but there are options there. Silicon is like a very cheap and convenient thing to use, so we just use test grade silicon wafers. So this in the center is actually a SEM sticky, the standard SEM mount. And so that's nice because it provides like a very good thermal contact and it mounts the piece flat, and there's no exposed like organic material that can be etched. And so usually these stickies, I can use them several times and then I just scrape it off and put a new one down. So I have here, this chip is a silicon wafer that was coated via magnetron sputtering with alternating layers of copper and silicon. And the thicknesses of those layers are about 50, well, it depends on the layer. They're 20, 40, 60 nanometers thick. And so the point of this is that it simulates kind of like a M1, M2, M3 of an actual logic chip. And the last step is this clamp ring, which holds everything in place. So this sometimes needs a little bit of finesse to get it down, and then there are 4 screws. And so the pressure from this clamp ring is also important for getting good thermal contact. So I'm doing the screws not fully tight at first, and then applying a little bit of pressure to make sure the pressure is even, but not high enough to crack the wafer. So now this is ready and mounted. I'm going to now close the load lock. I click the close door button, and the first thing it's going to do is it's going to close the shutter and it's going to home the stage so that the angle is repeatable every time. And I have to press these two buttons for my own safety so that the door can close. Now that the door is closed, I can do the pump sequence. Okay, it's currently pumping down and the crossover is 80 millitorrs. So while we're waiting for it to get there, I'll walk through the UI. So starting here is a visual overview of the chamber, and here's a side view. As we insert the sample later, this will actually animate and go in. So it gives at a glance an overview of what's going on in the tool. The chamber base is currently at 4.3 on 8, which is a typical base pressure for this tool. Here gives the vacuum status, the angle, spin, temperature, and here's the gases. So all gases are currently off. When they turn on, these will be highlighted. The low lock pressure is here. So starting here, the operations screen, this is where you would run a recipe. So here's what the recipe editor looks like. It's built around sub-recipes. So sub-recipes, I'll open one as an example. Here's for etching at 220 degrees. So first it goes to the etch condition and waits for 30 seconds, and then it actually does the etch with the shutter open. So this is 2 columns, and the usefulness of the subroutine design is that then you can chain together recipes. So my actual recipe for that 220 degrees is going to look like this. First, there's a pre-run, which conditions the chamber and starts the sources. Then it does my etch I define, and there's a post-run, which does the cool down of the neutralizer filaments. So that's the recipe I would actually run. Today, we're not going to be running a recipe. I'm just going to be running it manually, but we are going to record SIMS data. If you run a recipe, it is possible to actually endpoint on the SIMS data. So the rest of these tabs are for manual control. Here's for vacuum control of the main chamber for maintenance, the load lock, the pumps for starting and stopping, and the isolation valve. The etch source, I'll show this later. You can turn on and off the source here. You actually don't have direct control of the source, but you just put in the parameters you want, and the machine itself handles the starting and stopping and gracefully going from condition to condition. So under fixture control for manual control, so as I said, the angle, it's fully from 0 to 90 degrees facing the source and facing perpendicular to the source. The spin is from 10 to 50 RPMs. There's a substrate shutter, which is a clamshell type and protects the piece at all angles. And the linear rail is actually the piece that moves it's the arm that moves the piece in and out of the chamber. And then this chiller is because most of the tool uses house water, but it has a dedicated chiller just for the stage so that you have good repeatable control of the chuck temperature. So hide is the SIMS control. And this maintenance tab is for manual overrides for maintenance and also configuration. All right, so in just a couple minutes, we've reached the crossover pressure. So we're ready. So this tool doesn't have its own turbo for the load lock. Instead, it just opens into the main chamber. So I'm going to do that now. I'm going to press vacuum, isolation valve, open. And so now the 2 chambers have become 1, essentially. And you'll see the chamber pressure jumps up into the 5 scale. And within 5 minutes, it's going to be in the low 6. So now here's the interesting point of this tool is that so that chuck that we mounted the sample to, instead of transferring, a carrier into the chamber, the entire chuck is going to go into the chamber. So I'm going to do that manually by going to Fixtures, Linear Rail, and Extend. So now the piece is going into the chamber. So you can see that as the piece goes in, there's a little bit of animation here. This uses an encoder to show you how far it's gone in or out. And this also, the chuck gets larger as it comes in. All right, so it's finished inserting the sample. So now I can get it ready to do the etching. All right, so I'm going to set this at 220 degrees, and that's actually 50 degrees relative to the source. And the reason for that is 0 degrees is defined as flat, and the chuck is going to spin actually towards us, away from the source, all the way around, such that 270 degrees is facing towards the source. So we're going to go short of that at 220 degrees because that is the angle for which silicon and copper have the same etch rate. So now it is rotating. You can see it on the screen. It follows along with what it's doing physically here. This entire thing will come around. So while I'm waiting for that, I'm going to turn on the spin. I'm going to go at 50 RPM. So a typical spin rate is 20 to 50 RPM. And I'm going to leave the shutter closed for now because what I'm going to do is light the source. So as I said, like this clamshell type shutter will protect the piece at any angle. So it's okay to light the source now. I'm going to first light the PBN. So I'm going to give it 20 skims and 1 amp. So PBN stands for plasma bridge neutralizer. It's providing electrons to compensate for the ions that are coming out of the source. So typically the current that you need is at least equal to the source current. Today I'm going to run with only 230 milliamps out of the source, but I'm going to give 600 milliamps from the PBN just to make sure everything is nicely compensated. If you have excess electrons in the chamber, they're very light and mobile, so they'll discharge on anything, any surface that's charged, they'll just discharge to, or to the chamber walls. But what can happen is if you have excess ions in the chamber, you can charge up your sample and then the etch rate will drop to like 1/10. So I'm going to light the source now. I'll give it 20 skims. I'm going to do 600 volts and 230 milliamps. And the accelerator voltage is a dependent parameter which doesn't affect the process, and that's for this source and grid set is 90 volts. So I'm going to press ignition, and it's going to go through its automatic ignition sequence. It already completed it actually, but what it does is it first turns on the beam voltage, which is a positive voltage, and that pulls in electrons from the PBN, which helps ignite the plasma. And once it detects that the plasma is lit, it's going to turn on the accelerator voltage, which is a negative voltage. So once the accelerator voltage is on, there's no longer electrons from the PBN entering the source. And so then you can see we have here the beam current. It took about 10 seconds for it to reach its final current setting that I asked for. So after ignition, it's going to slowly adjust the RF power to the power required for the current you asked for. I told it to start at 300 watts, so it did, and it got about 100 and some milliamps. And then it had to ramp up slowly to 370 watts in order to reach 230 milliamps. So you'll see here the reflected power is quite high. It's 60 watts. And the reason for that is because as this tool accumulates hours, the etch products are actually coating the inside of a quartz chamber inside the source, and that is reflecting the RF back. And so the solution for that is you can either just run oxygen through the source for about 10 minutes and you'll see this drop to about half of what it is now. But over time you will have to, after like 200 to 300 hours, you will have to remove that bowl, clean it, and put it back in. That's a pretty quick maintenance job because you do have to vent the main chamber, but the bowl comes out very easily with a total of 8 screws, and then you can put it back in. Okay, so now that the source is lit, I'm going to turn down the gases to the actual process condition. That's 600 milliamps and 6 SECM argon through the neutralizer. I'm going to turn this down to 12 SECM through the source. I gave it a little extra gas just because it helps it light, but now that it's lit, I'll turn it down. Actually, the SIMS likes the pressure to be as low as possible. You also see like the reflected power drop considerably. So the source and the SIMS both like the gas to be as low as you can make it while the source is still stable. So the source is on, but before I open the shutter and start etching, I'm going to start the SIMS. So the SIMS is run off of a different PC. There's actually a rack unit which controls the SIMS directly, and then that rack unit talks to this software here which runs under Windows. So today I'm going to run a time scan, which they call mid mode. And I guess the last time I ran it, I was looking at tungsten. Today I'm going to set up copper, which is at 63 AMU approximately. This SIMS is not super high resolution, so it doesn't matter if you write 63 or 63.07 or whatever the exact mass is. So the other material on this chip is silicon, but unfortunately you can't monitor silicon because its mass is 28, which is the same as background nitrogen. So N2 is 28. So if you tried to monitor silicon, you would just get a very high signal, which you can't really see the silicon start and stop. So I'm going to delete that row, and we're just going to look at copper. So I'm going to press OK. So it's not collecting data yet. There's one thing I want to do to edit this recipe. So this is the recipe. I want to change the acquisition time to 300 milliseconds, which reduces the noise a bit in the signal. All right, so now this is ready. I'm just going to press go, and it's going to do its initialization, and you'll see it start collecting data. All right, so there's the data. There's no copper being etched right now, and we're seeing a signal of 1800 counts, so that can be considered the background level. The background level will go up and down as the vacuum in the chamber goes up and down. So if you want the highest resolution, you actually have to wait about half an hour after transfer before etching, but we don't need that today, so I'm just going to get started. I'm going to go back to the tool control computer. So the source is on, the spin is on, the angle is correct, the gases are correct, the vacuum looks correct, everything looks correct, so I'm going to go ahead and just open the shutter. So now if we go back to the SIMS data, every time you open the shutter, there's always this initial spike. So the top layer on this sample is actually silicon, so we're still not seeing copper. So you'll see the quote-unquote background level actually goes up and down under a lot of conditions. It's dependent on vacuum level. It's dependent on basically how many ions of any type are entering the SIMS head. So with our etch active, we're getting a little bit more ions into the SIMS head, even though they're not copper, and the background level is now approximately 4,200 counts. So this stack is, it starts with a silicon layer of 120 nanometers thick. So at these conditions of 600 volts and 230 milliamps, it etches through about a micron of material in about 10 minutes. So that's going to go through the 120 nanometers of material. It went through in from about 50 seconds up until 2 minutes. So that's 1 minute and 10 seconds to go through 120 nanometers. And now we're seeing the real copper signal. So you'll notice that there's a transition region, which is about 4 seconds wide. And then you see this peak and then a plateau, and then a peak again. So these peaks are because, so oxygen has actually a lower sputter yield than argon atoms. So sputter yield is how many ions you get, or how much material you're removing for each incident ion. So in the case of oxygen, the sputter yield is lower, but it produces way more ions than argon. So the actual amount of atoms coming off are less, but the number of ions are much higher. So what happens is that because of the way we deposited the sample, there's a little bit of oxygen at the interface between each material. So in between copper, well, copper is here and silicon is here. In between each layer, there's a little bit of oxygen that got absorbed while it was waiting for the transition to the next material layer. So this peak here is because of that oxygen basically enhancing the copper signal. You can also run oxygen through the source itself, and you can see the signal goes up. It depends on the material and your etch conditions, but it can go up 2x or it can go up 10x. So that's one method where you can actually enhance the SIM signal for if you have a very small chip, or you have something like a material that's very thin layer, or there's not very much of it, and you want to enhance the signal. You can try and add oxygen through the source itself and enhance the SIM signal. So right now we're getting a signal at the copper layer is about 38,000 counts per second, which is a pretty good level. That's well above the background of 1 or 2,000. And so that is from a chip which is approximately 1 centimeter by 1 centimeter in size. So you can kind of scale that down. A chip that's 2 by 5 millimeters, you can still observe the copper signal. So this chip has a copper 50 nanometers, that's this one. Next is silicon 60 nanometers. Then there's copper 50 nanometers, silicon 60 nanometers, copper 40 nanometers, and this is silicon 20 nanometers. So even with just 20 nanometers in between the copper layers, it drops almost to baseline, and there's good separation between the layers. So this is the last layer, which is another copper 40 nanometers. So after that finishes, this chip will be done. All right, so we came down, so we're fully through all the copper layers that I put on this chip, and you'll see it drop back down to baseline. And so now that I have all my data, I can just press stop scanning, and I'm going to press to stop the instrument so it turns off the SIMS head. I'll go back to the tool, and I'm going to first just turn off the source. And then I'm going to go to operation and do the automatic unload. So that's going to actually correct the angle. It's going to close the shutter, and it's going to pull out the tool and close the ISO valve, and then wait for me to vent the tool. All right, so I can hear the ISO valve closing. So that completes the automatic unload sequence. And just to show you the chip, I'll just quickly vent and open the load lock again. So the door is opening. and here's the etched chip. So sometimes the shutters and the stage and the clamp ring can be a little warm, but the chip itself feels cool to my touch, so I can take it out right away. So there, now it's just a bare piece of silicon. All the copper layers are removed. Okay, let me go back to the SIMS trace so I can talk about how you would set up automated endpointing. So you can see here there are 5 distinct copper peaks for the 5 layers. And the way you can define the endpoint is either on rising edge or falling edges. And you can also count layers. So let's say this is M5, 4, 3, 2, 1. I want to end somewhere here in what would be via 3 because I want to image M3 in the SEM. So the way I would do that is to say, okay, let's look at falling edges. And so what you want to do is you have to etch one chip first so that you know what your signals levels are. You can see here that it's about 30,000 counts, gets you above like the layer, but well above the baseline. So what you're going to do is you're going to find a recipe that says, okay, once I get above 30,000 counts, I'm going to start looking for the falling edge. And it's going to say, okay, mark falling edge number 1. But I want falling edge number 2. So it's going to keep waiting. Oh, it went above 30,000 again. Now let's look. Okay, falling edge number 2, mark. And then I want to be somewhere in the middle of the via layer. So what I know is that in between this point, so let's say I want to end right at 4 minutes, which is in the middle. So in between this point, which is 30,000 counts, is 3 minutes and 42 seconds, and 4 minutes, that gives me 18 seconds. So I'm going to tell it to go look for the second falling edge and then wait an additional 18 seconds. And then this SIMS controller is going to flip an input on the PLC and etching will stop immediately. It will turn off the source and close the shutter. So there's a slight delay from closing the shutter. That's why we have this sort of immediate communication from the SIMS controller and the PLC, and it will turn off the source. That's the quickest way to stop your etching, so it can be quite accurate. Then I can take my piece out and image it. The other nice thing about ion beam etching is that it's very repeatable. Even if you just run on time alone, you will get something like 1% error or better. So I could even just run this on time. I can say like, okay, from this point of shutter open, which is at 51 seconds, up until 4 minutes. So that gives me 3 minutes and 9 seconds. I'm just going to etch by time, and you will get that within 1%, which is probably sufficient if your goal is just to do SEM imaging of M3 in this case. But also what that means is that I can stop here, take the chip out, image it, put it back in the chamber, and start etching again, and it's like I never took it out. It will continue and produce this exact same kind of SIMS trace. All right, so that's it for the demo today. We just wanted to demonstrate that we can delayer a sort of dummy logic chip with copper and silicon layers, and the copper layers are as thin as 40 nanometers, and their separation is as thin as 20 nanometers, and yet we can still resolve them, similar to an actual logic chip.
So thank you, Kyle Godin of Denton Vacuum, for that excellent presentation. We'll now start taking questions. We have a few of them in the queue already. In fact, quite a few, but there's still room for some more. Please use the questions tab to enter your questions. We will get to as many as we possibly can in the time that we have remaining. So let's move on to our first question. What is the beam size when you etch the chip?
Yeah, so like I described, so the ion source is actually quite broad. So when the beam hits a substrate, it is actually larger than the 100 millimeter chuck. So across the chuck itself is about plus or minus 3% uniformity. So yeah, the beam is larger than 100 millimeters, and you do get 3% uniformity over that 100 millimeter chuck.
Okay, our next question is, I can see that you use the film sample. Have you delayered a pattern sample or real semi-chip? If yes, do you see any difference?
Yes. So we chose to do a sort of like this dummy logic thin film sample today because the results are much cleaner. So we've actually delayered a lot of different kinds of chips, memory chips, logic chips, like 28 nanometer, 40 nanometer process, and also like advanced node stuff that is kind of proprietary from our customers that we're working with. And what you see is, you know, when you get to the actual logic chip, there's a lot of challenges that makes this, you know, something like the SIM signal, it's not as clear of a separation between layers. But what this like thin film sample shows is that it's not about the thickness, right? So if you have something like an advanced node with, you know, whatever 20 nanometers in between metal layers, you know, that's not what's limiting our ability to delayer the chip. Like we can clearly resolve that when we have a very nicely prepared sample. So the kind of the challenges we're facing with actual logic chips is so something like you know, in this case, I know that the materials are copper and silicon, and it's exactly the same copper and silicon as I do my sort of like etch versus angle testing. So I know the exact etch rate. Now, when you get to like an actual logic chip, you know, the materials are not exactly the same. So the copper is not, I was using magnetron copper. It's like a different kind of density, slightly different etch rate. And even they have stuff like, you know, there's the high K dielectric with silicon oxide impregnated with carbon. There's a lot of different materials that go in there. So what we see is that as you start etching, as long as you start with a very planar surface, we can keep it pretty planar, but by the time you go through a couple microns of material, you know, you might have a non-planarity that's a little bit larger than the actual layers themselves. So that's what kind of in the presentation, and I showed those images of what was supposed to be M1, but really, if you take your SEM and zoom in and move around, there's bits of like M2 there, little pockets, and that's the level of non-uniformity you get from an actual logic chip. So we are currently, you know, investing our time and resources into those kind of challenges, but that's kind of our state of the art.
Great. Thank you, Kyle. I'll remind our audience that we're speaking with Kyle Godin of Denton Vacuum. Our next question, and Kyle, this one gets a little complicated. I don't know if you want to open up the questions panel of the webinar player just so you can follow along with me. Did you try to monitor the mass 103 AR plus CU? This may help reduce the spike at the interface, similar to the idea of CSM plus in-SIMS technology.
Okay, yeah. You know, that's actually, I have not tried that. There is one thing we do, which is, you know, like I said, you can't really monitor silicon, but you can monitor SiO, and we do see a signal from that. So if you take a logic chip, you can look at aluminum, copper, SiO, and tungsten. You can, and tantalum. You can see all those as you go through the chip. But yeah, thanks for the tip. We'll definitely try that.
Okay, our next question, do you get cupping where metal vias are stacked and cause uneven clean?
So yeah, there's basically if you end up with, I'm not sure what you mean by cupping, but that's kind of in my mind, what I'm hearing is like it's non-uniformity, right? So if especially the upper metal layers, like let's say in current nodes, it's like M16, M17 can actually be quite thick, more than, I'm blanking on the thickness, but it's more than 400 nanometers. And so if you go through that and you have, you know, something like you don't have your exact selectivity dialed in, then yeah, you're going to end up with non-uniformity by the time you finish that. And that's something where that's basically what we're seeing then, because if I can delayer the dummy logic chip and it looks perfect and clean, then when I go to the real chip, and let's say I just go, because I've done this, right? Because I want to make an automated recipe. So I first take a chip and I just go through the whole chip down to the silicon. And because I want to capture the SIMS trace, and then I can use that SIMS trace when I etch the next chip to stop exactly where I want to, because I know what the SIMS trace is supposed to look like. And so I have that chip where it's down to the silicon, right? And there's like a ghost pattern of several of the metal layers, especially, you know, the higher up ones that are thicker. And that is entirely due to the not quite perfect selectivity. And so yeah, I don't believe that's like an insurmountable challenge, but it's definitely, it's not perfect from what we have right now. So if it's, you know, so if you have a place where, you know, let's say you have like M17, M16, M15, and just by chance, there's a place where they all have like copper in the same section, and your copper etch rate is too slow relative to your dielectric etch rates, then yeah, you're going to end up with like a pretty thick pad there. But you know, you should be able to dial in the selectivity to 0 just through process development.
So we had one that came in that's kind of a follow-up to that last question. And I'm not sure, the first word is even, but I wonder if it might mean ever. But regardless, I'll read it the way it was written. Even try to monitor the mass 68 SI plus AR.
No, yeah, we haven't done that either, actually.
Okay. Our next question, how do you first planarize a chip that has a upper metal layer that is not planar?
Yeah, so that's another challenge with this process is that, you know, like I said, the ion beam, it's the selectivity is very low. You know, even like you have something like these, which is a benefit in a lot of cases because it's, you know, it's possible to dial in the selectivity to be 0 so that you're etching the traces and the dielectric at the same rate. And also that means like if you have these diffusion barrier layers with tantalum or tantalum nitride, you know, so it's just going to go right through those. It's not going to get stuck there and take minutes to go through it. It's going to go through those, and it might take, you know, twice as long as the other parts of the material. But you know, it's only 10 nanometers thick, so the non-uniformity that generates is not that bad. So then, but you know, so what that means also is that because you can't, there's no like tilt or gas chemistry where you can say, you know, I need to correct the non-uniformity that exists in a chip before I etch it. Like the chip has to start very planar. There are some things you can do. Like I've seen, I mean, I've done demos also where we receive chips and it's been, so the typical thing is you have to, you know, decap it, like, and deprocess it down to a certain point, usually using like CMP or just mechanical polish. And that will then you just bring it, you know, because like the last layers, especially like the SiO2 capping layer, is very non-uniform. So you got to just bring that down to something like M17 approximately. And then what we've seen is like if people use CMP to come down to M17 and try and make it planar, usually the metal layer ends up slightly thicker than the dielectric, just like pretty uniformly across the chip, as verified by profilometer measurement. And so that can actually be corrected because it's like, okay, so I know I have, you know, 80 nanometers of excess copper to go through. So I can use my etch versus angle chart to say, okay, I need to go through 380 nanometers of copper in the same time I go through 300 nanometers of SiO2, and then the chip will become planar, and then I can change to my normal angle and continue. So that kind of non-uniformity can be corrected when it's like a material-dependent non-uniformity. If it's just like a general non-uniformity, like you're inside of a, you know, a thick dielectric layer and there's non-uniformity, the tool doesn't really have the ability to correct that. It has to be corrected with mechanical polish or something before you do ion beam.
Okay, remind everyone that we're speaking with Kyle Godin of Denton Vacuum. Our next question, can you change your voltage? What is the highest voltage you can apply?
Yeah, so for these kinds of sources, the typical voltage ranges from 50 to 1,500 volts, and the actual ion energy is slightly lower than the voltage you apply to the grid, maybe 15 to 25 electron volts below your actual grid voltage. And so what you'll see is when you go from so there's a transition region because the sputter threshold of most materials is between 15 to 35 electron volts. But really, as you're close to the sputter yield, so different materials have different, sorry, not sputter threshold. I think I misspoke just then. So different materials have different sputter thresholds. And when you're down there near the sputter threshold, or even up to 150 volts, then that's another way to play with material selectivity because there's a big change between material etch rates as you change the ion energy in that range. Once you get above 150, 300, 600 volts, then you have much less ability to play with the selectivity. Instead, you're just going to increase the etch rate as you go up in voltage. So if you want an extremely rapid etch rate, then yeah, it's available to you to do something at least 4 or 6x higher than our typical results at, I usually run around 600 volts and 230 milliamps are, yeah, so the actual current, the actual ion flux density on the substrate is 1 to 2 milliamps per square centimeter. And you get this kind of etch rate, like I said, where you go through a micron in maybe 10 minutes, depends on the material. But so you could drive the tool to a much higher power and get maybe 4x that etch rate, and that would be your upper limit.
Okay, our next question is, what area is the SIMS signal coming from?
So the SIMS has, just because of the way the head is designed, it has an aperture, and also then there are 2 voltage plates that steer the ions into the head. And then the reason for that is because there's, compared to a typical metrology SIMS, there is so much material coming off of the piece that it's going to quickly coat the entire inside of the SIMS and make it non-operational. So that aperture and those voltage plates kind of already dramatically reduce the amount of ions that are actually coming into the head, and also they provide this sort of directionality. So the SIMS head has an acceptance angle of about, they say 30 degrees for and what that translates, if you look at the actual response versus incident angle though, it's really sampling the center of the chuck. So that's where the tool is designed such that the SIMS head is sort of in front of the chuck, looking at the center. And then as you tilt the chuck from facing the source to being at some oblique angle, the center of that axis of rotation is fixed on the center of the piece. So the sort of geometry there is fixed between the SIMS head and the center of the chuck, and that's where the signal is coming from. It's really just the middle centimeter of the chuck.
Okay, we're coming up against the end of our session here, but maybe we can squeeze in 1 or 2 more. Our next question is, what type of thermal pad was used between the wafer and the chuck?
Yeah, so that thermal pad, I'm not 100% certain, but I think it's silicone that's impregnated with boron nitride. I'm pretty sure that's what it is.
Okay, maybe I think we have time for 1 more. Have you tried other etch gases, and what was the result?
Yeah, actually, so we don't have a lot of process data with additional gases. So we have some of our customers who have this tool, they have tried fluorinated gases and regularly use them, but we don't actually have process data for those. But the tool is fully capable of doing it. We just don't have the scrubber here in our facility. So we've been sticking to oxygen and argon.
Okay, great. Well, thank you so much, Kyle Godin of Denton Vacuum. Unfortunately, we're not going to be able to get to the last one or two questions, but in a few days, all of our participants are going to receive an email with further contact information. I certainly encourage you to follow up with Denton for more information about today's topic. Kyle, thank you so much. That was a marvelous demonstration.
All right, thanks everyone for joining.
So once again, I'd like to acknowledge the sponsor of today's webinar, that's Denton Vacuum. Denton Vacuum provides innovative deposition and etch equipment solutions built on standard platforms for any production level, from pilot production to high volume manufacturing. Find out more at dentonvacuum.com.